We can modify the ideal gas law to include some different variables, like density and molar mass. On this slide, I'm going to show you the proof to go from the original equation, PV equals nRT, to the new form of the equation that includes density and molar mass. We start out with the ideal gas law, PV equals nRT. We can divide both sides by RT and divide both sides by V to come out with N over V equals P over RT. Then we can multiply both sides by the molar mass. We represent molar mass with a squiggly capital M. Remember, molar mass is usually grams per mole, or mass per mole, if you will. We can rearrange that to say that molar mass times moles equals mass. When we have our squiggly M in the numerator and N in the numerator being multiplied together, that's molar mass times moles. So instead of writing squiggly M and N, we can write mass. Now we write mass divided by volume equals P over RT times the molar mass. Since mass over volume is density, we can write density, D, on the left side of the equal sign. On the right side of the equal sign, we have pressure times molar mass divided by RT. This is a new form of the ideal gas law that we can use. It depends on what type of variables we're trying to solve for as to whether we'd want to use the original form of the equation or this form of the equation. Something to keep in mind here is that the mass is in grams and volume in our ideal gas law equation is in liters. Therefore, we would have grams per liter as the units of density in this equation. Grams per liter is a common unit of density for gases because they take up a lot of space. Here's an example using the modified ideal gas equation. We have a gas that was found to have a density of 0.0847 grams per liter at 17 degrees Celsius and a pressure of 760 torr. We want to find the molar mass of that gas, and based on its molar mass, we can identify the gas. We want to make sure our units are correct before plugging them into the equation. Density is given to us in grams per liter, which is an appropriate unit. Pressure is given to us in torr, so we need to change it to atmospheres to match our ideal gas law constant R that has liters atmospheres per mole Kelvin. We do that by dividing by 760 and come out with 1 atmosphere. We need to change temperature to Kelvin, so we take 17 degrees Celsius, add 273.15, and that gives us 290.15 Kelvin. Before plugging all of those values into the modified ideal gas equation, D equals P squiggly M over RT, we want to rearrange that equation to solve for molar mass. We multiply both sides by RT and divide both sides by P. Our rearranged equation becomes molar mass, squiggly M, equals dRT divided by P. Now we can plug in our values, making sure that we've used the correct units. And that gives us a value of 2.02 grams per mole. We know hydrogen atoms have a molar mass of about 1 gram per mole. Helium has a molar mass of about 4 grams per mole. It can't be helium because that's too big, and it can't be just one hydrogen because that's too small. The only possible identity is for it to be H2 molecules. What is the density of O2, the oxygen molecule, at 37 degrees Celsius and 2.3 atmospheres? R equals 0.08206 liters atmospheres per mole Kelvin. Is it A, 2.9 grams per liter, B, 0.020 grams per liter, C, 270 grams per liter, or D, 1.8 grams per liter? The correct answer is A, 2.9 grams per liter. We're using the modified ideal gas equation. Density equals pressure times molar mass divided by RT. Remember to get your temperature in Kelvin. Also, we're using the identity of the gas, oxygen, the O2 molecule, to get the molar mass. We would use 2 oxygen atoms from the periodic table. You can plug those values straight into the equation because density is by itself on one side of the equal sign.